And the next presentation is on fast reactor physics by Konstantin Mikityuk.
Thank you very much, Mr. Chairman. Good morning, everybody. First of all, on behalf of Fast Reactors Group at Polshar Institute, I would like to thank organizer for giving this opportunity to present several topics at this very high-ranked conference. And during the next 20 minutes, 25 minutes, I would like to present you some aspects of fast reactor physics, especially related to utilization of thorium. So, few introductory words about features of fast reactors, fast reactor spectrum. A bit historical overview about fast reactors. And current situation, I would like to very briefly show you a few projects currently running in Europe in which we take part. And then the second part, I want to emphasize a few aspects considering the question, could thorium become a fuel for fast reactors? From different point of view, and then summarize. Okay, fast critical reactor is a reactor where the fission chain reaction is sustained by mainly fast neutrons. So we don't use moderator for this reactor, and these two charts shows an examples of unit cells for sodium fast reactor and pressurized water reactor, emphasizing the difference in the amount of coolant or moderator in two cases. And also this chart shows the flux or spectrum as a function of neutron energy. In red, we have sodium fast reactor with majority of neutrons in a region above 10 keV, and pressurized water reactor, typical thermal spectrum. The concept of breeding is production of new fissile isotopes in the nuclear reactor. It's a kind of transmutation which allows us to convert fertile thorium-232 through N-gamma capture and to beta decays to uranium-233, which is fissile, and also uranium-238, again, N-gamma, and 2 decays to plutonium-239. So fertile and fissile isotopes. So if we write the very simple neutron balance and critical reactors, then we can arrive at the equation which you already saw several times during this conference. So the eta is equal to 1 neutron, which we need to continue chain reaction. Breeding ratio, which is the number of fissile nuclei created per fissile nucleon destroyed. And the total loss rate, which includes parasitic absorption and leakage. So in fast reactor and fast spectrum, we are trying to increase this breeding ratio, and we can do it by decreasing the losses. So we need tight lattice, we need high power to decrease this factor. But what we should remember also is that in fast spectrum we have contributions from fertile fissions. And in a way we can interpret it that we can reduce this one. We don't need exactly 1 neutron from fission of fissile because we have contribution from fissions of fertile. Okay, again, I put spectrum here and dependence of eta on for different isotopes. We can see that best for breeding, the beta neutron economy is provided by plutonium-239 and fast spectrum. Then We have uranium-3, a little bit worse situation, and uranium-5 is the worst. So that's why fast reactors was started with plutonium-9 fuel. And in a way, the breeding, we can interpret it that fast neutron spectrum allows us to efficiently burn fertile uranium-238 or thorium-232 via transmutation to fissile isotopes. Normally, if the breeding ratio is more than 1, the reactor is called breeder, and when breeding ratio is exactly 1, it's called isobreeder or break-even core. Just a reminder that the first reactor which produced electricity was fast reactor in 1949, EBR-1, Argonne National Laboratory. The fuel was based on plutonium cooled by liquid sodium. Then starting from this moment, okay, in fact, the first fast reactor was Clementine cooled by mercury. And then the development of new reactors along the time was relatively smooth with some breaks. The biggest break was between Monju and Chinese experimental reactor. And you can see also that we have currently a number of reactors working mainly in Russia, India, and China. The Generation 4 International Forum is a cooperative international endeavor organized to carry out the R&D needed to establish the feasibility and performance capabilities of new reactors, next generation reactors. So 9 countries joined and signed the GIF Charter in 2001. Next year, Switzerland joined, originally in the area of gas-cooled fast reactor and high-temperature reactors. And then Euratom, China, and Russia also joined this club. 6 nuclear energy systems were selected, and 3 of them are fast reactors cooled by gas, helium, sodium, and lead. But the last one, molten salt reactor, is considered in different options, including fast spectrum, and it will be next presentation. The keyword, the goals of Generation 4 are listed here: sustainability, safety, economics, reliability, proliferation resistance, and I'm going to touch very briefly some of them. I would like to show you a few R&D projects related to fast reactors currently running in Europe. Of course, the first, the most promising one is sodium-cooled fast reactor. There is a big program called ASTRID in France for development of new fast reactor at Marcoule site. But also there was a project called ESFR Euratom, supported by Euratom, where a big consortium of European countries developed a concept design of 3,600 megawatt thermal reactor, fast reactor cooled by sodium, fueled by mixed uranium plutonium oxide and stainless steel cladding. And I put here the main parameters. The second project also underway currently is called ALFRED. There is a consortium of several countries led by Italy, and they are developing a demonstrator of lead-cooled fast critical reactor technology. So it's 300 megawatt thermal, cooled by pure lead without bismuth, and again the same fuel. And for the gas-cooled fast reactor, there is a project called Allegro. Again, there is a consortium of Eastern European countries, including listed here. And it's also a demonstrator, small power, 75 megawatt, cooled by helium at 70 bar, the same fuel. If you look at the problems, main problems, probably 1, 2, which we have for this reactor. For sodium reactor, the main problems are the chemical activity of sodium, but also neutronic problem is a potential positive void effect, means when we remove the sodium from the core, the reactivity can goes up. And we can consider this when we look at sodium and as possible alternative of current fuel. For the lead fast reactor, the safety is significantly better compared to others due to properties of heavy liquid metal. But there is an issue of normal operation, like interaction with structural material, corrosion, and so on. And for gas-cooled reactor, evident problem is decay heat removal in case of depressurization situation. And for this reason, you can see that in the design, we consider a closed containment, which is practically another pressure vessel, in order to improve decay heat removal in accident conditions. So we saw that sodium is not considered currently, and the question is, could it be a fuel? And first, if you look at sustainability, we can say that according to our current knowledge, current calculations, the fast reactors can operate in equilibrium closed uranium-plutonium cycle with breeding ratio equal to 1. Which is isobreeder and which are fed only by depleted or natural uranium. So this is a input, this is closed cycle, which includes radiation, cooling, reprocessing, and fabrication. And this is output, and in some ideal situation, we can consider that input is only uranium-238, output is fission product only, plus losses, of course. And we did a very simple model of this closed equilibrium fuel cycle in order to evaluate progress or evolution of feed fuel, which is uranium-8 in this case, in equilibrium situation, some ideal situation. What will be the picture, the shape of different isotopes. So we did this balance and calculated the fission rate, so normalized, for example, 2,000 atoms per second, and we can see what is the fraction of fission for different isotopes in this idealized situation. Then we can ask, could the same reactors operate in an equilibrium closed thorium cycle? Thorium-uranium cycle. And again, according to our calculations, the answer is yes. But the evident problem is that we don't have uranium-233 available as a main isotope. And this is one of the first thorium disadvantages. So the question is how to start thorium reactor, fast reactor, what fissile material to use, probably plutonium, probably uranium-235 or uranium-233 generated somewhere else. These are all questions for which we don't currently have a clear answer, and this is nice research to make. Nevertheless, we looked at equilibrium cycle, assuming that we managed to start the reactor and see what will be the picture for equilibrium, this simplified equilibrium. And as everybody knows, and we managed to burn all input nuclei before we reach higher minor actinides. Okay, we still have some small amount of neptunium here, but very negligible amounts of higher actinides. And this is a clear advantage, so the very low amount. On the other hand, there is an end-to-end reaction for thorium-232, especially higher in fast spectrum, which produce thorium-231 decay to protactinium-231, again N-gamma and decay to uranium-232, which is a precursor of gamma, hard gamma emitters. And this is a clear disadvantage from viewpoint of protection during reprocessing, and also decay heat and radiotoxicity of equilibrium fuel. I put here the resulting vector of composition corresponding to this simplified equilibrium cycle for uranium cycle and thorium cycle in logarithmic scale. Here it's mass fractions. So it's interesting to see that the shape is somehow similar. So this is a fertile fuel, uranium-8, and thorium-232. In thorium case, it's slightly higher, the equilibrium fraction of fertile fuel. And fissile fuel is very close, around 10%. And then we have a tail, longer in case of uranium and shorter in case of thorium, because in this tail we have very good fissile material, which allows us to avoid propagation of our mass flow to the higher actinides. Then we can also look at the neutron balance, and here I made the charts again for uranium and thorium cycle, putting in blue bars isotope-wise contributions to absorption. So for every isotope, for example, for uranium-8, we can say that about 40% of all neutrons are absorbed by uranium-8, and so on, and something like 40% by plutonium-9, and finally we arrive to 1, normalized to 1. And the red bar shows us the contribution of different isotopes to fission. To production, like 20%, almost 20% of all neutrons produced by fission of uranium-238. And then the biggest fraction, of course, is from main fissile, but also contribution from other plutonium isotopes. And finally, we arrived at K infinity because we analyzed in this simple model. We neglect the leakage effect. And the same we did for thorium cycle. We can see here that uranium-233 is better fissile material compared to plutonium-9. But another disadvantage is that fission rate of fertile isotope thorium-232 is significantly lower compared to uranium-238. And the combination of these effects resulted in lower K infinity for thorium cycle. And this is another disadvantage. From viewpoint of safety, we can look at just two reactivity effects, Doppler effect and void effect, especially for sodium. This is the most crucial thing. But please have in mind that in fast reactor, there is a number of reactivity effects which are probably less dependent on fuel type, and these are thermal expansion effects. So I did an illustration here and put different structures like core, control rods, diagrade, strong back vessel. And we have very breathing organism which expands when temperature changes. Then it expands in different direction and results in differential movement of absorber and fuel. And these effects, as I said, are probably less dependent on the fuel type. For the void reactivity effect, we have two components, which is spectral hardening component and leakage component. Both strongly depend on the position. It's three-dimensional effects, and we will look only at spectral hardening. So what we did for this simple model, we calculated two effects, void effect and Doppler effect for infinite medium. So, and for Doppler, we calculated the effect from nominal temperature to melting temperature, which is in a way the maximum possible Doppler effect, and for void also maximum possible from nominal to 0. This is sodium fast reactor. And then I plotted void effect versus Doppler effect and did simple isotope-wise decompositions like this, so normalized to the same production. So we can see only effect of change of absorption in this approach. Nevertheless, so this point is the final value of void effect and Doppler effect for thorium. And this point is a final value of void effect and Doppler effect for uranium cycle. So clearly the advantage of thorium cycle demonstrated here is stronger Doppler and weaker void effect. Quite significant. I don't have at the moment the explanation why Doppler effect is stronger in equilibrium thorium cycle. It would be nice research to answer this question. And we can discuss if somebody has the answer. But weaker void effect, one of the explanation can be, again, ETA chart. So if you look at the spectrum, that the removal of sodium basically means spectral hardening. It means that the flux shape will shift to the right, to the higher energies. And in this region, we can say that ETA is growing faster for plutonium-9 and more flat, or goes up slower for uranium-233. And this is one of the main explanations of lower, weaker void effect in thorium-fueled sodium-fast reactor. There is another issue related to proliferation resistance as one of the goals of Generation 4 International Forum. Again, if you look at the transmutation of fertile isotope, we can say that the misuse of uranium-233 is protected by presence of uranium-232, which is the same element, difficult to separate, and which is predecessor of hard gamma emitters. But on the other hand, if we consider the precursors, immediate precursors of fissile, which is protactinium-233 and neptunium-239, in case of two cycles, we will see a very big, significant difference between half-life of these two elements, and potentially one should consider the danger of separation of protactinium-233, and then if we let it decay, then we have pure uranium-233, which is probably a disadvantage from viewpoint of proliferation resistance. We did for these two simplified equilibrium cycles analysis of radiotoxicity and decay heat. And it's probably not news that thorium cycle is characterized by lower radiotoxicity and lower decay heat up to a certain point in time, after which because of the decay and buildup of definite isotopes, the picture is changing, and radiotoxicity and decay heat becomes higher compared to uranium cycle after about 10,000 years. So I would like to conclude now. So the past and, okay, in terms of disadvantages and advantages, I have to slide. And this is not conclusion, this is only summary, so I don't want to conclude. I just want to make a picture. So past and current fast reactors were based on uranium-plutonium cycle, and operational experience with thorium-uranium fuel is very limited. The same that we have very small experience in fuel manufacturing and reprocessing, lower for thorium cycle fuel compared to uranium-plutonium cycle for fast reactors. So the fissile fuel for thorium cycle is not available. We should develop the procedure how to start the reactor Uranium-232 is produced, and especially in fast spectrum end-to-end reaction is more pronounced compared to thermal. And the K-infinity of equilibrium fuel is lower for thorium cycle compared to uranium-plutonium-1, and this means when we design the real reactor, it can mean that to reach isobreeding, we will need blankets of fertile material, which is, again, probably not good from a proliferation resistance point of view. And the fissile precursor of uranium-3 has higher half-life, again, what just we discussed. And I would like to conclude with advantages. So we see with our tools that fast reactor can work as an isobreeder and thorium cycle closed on all actinides. There is a very low amount of minor actinides in equilibrium thorium cycle. Doppler effect is stronger and void effect is weaker in equilibrium thorium fuel cycle compared to uranium. So it can be one of the ways how to improve safety of sodium fast reactor. And misuse of uranium-3 is protected by uranium-2, and radiotoxicity of sodium fuel is lower and decay heat. Thank you very much for your attention.
Thank you very much, Konstantin. Do we have any questions? Yes. Yeah.
Your system that you are studying is a 1,000 megawatt sodium cooled fast reactor? What
we studied, yeah, we used ESFR as prototype for this study.
But so coolant is sodium?
Coolant is sodium, yes.
You see, the problem with sodium is that you cannot avoid the positive Doppler coefficients. Superphoenix has $12, PFBr has $6 for 2/3 of the widening of the core, and your graphs are all...
Sorry, positive void.
Positive void coefficient. Mm-hmm. Yeah, 2/3 of the core, when you void, you get the maximum void. Your graphs are quite correct and in line with what we know. And it is about $6 for 500 megawatt PFBr and $12 for the Superphoenix. But people say we won't allow sodium to boil. We will give an office order. But this is one issue. If you take lead, you don't get the negative value. With thorium fuel, with the lead coolant, you get definitely negative void effect. Have you investigated that?
No.
Okay, that is one. The other thing is about the Doppler effect you mentioned, that the thorium Doppler effect is stronger than the U-238 Doppler effect. This is also well known, and the reason is attributed to the resonances. And we had done some study in India and published a paper in Nuclear Science and Engineering with one of my students I have done. We have seen the distribution of the Doppler coefficient as a function of energy. And you get a peak around 1 keV. In a thermal reactor or in fast reactor, the Doppler coefficient is really coming from resonances from 100 electron volts to 2000 electron volts. So the nature of the resonances in thorium give a better Doppler coefficient. So if you look at the individual resonance contribution, you can figure out the reason. So it's not a difficult issue.
Okay, I will ask you the reference to the paper. It's interesting.
Yes, we have a question there.
Yes. Yeah, thank you. Could you please project the conclusion? Yes, on each point. First, on the void coefficient, I would like to just to make some comments because the new design for the French S3, the future fast breeder reactor, will be designed in order to have zero void coefficient by replacing the axial blanket by sodium instead of having fuel. So this is the first point. New design of sodium-cooled reactor, we will not have a positive void coefficient. This is my
okay, we should be careful.
Almost.
You always should say the size of the reactor.
Yes, well, this is my second remark.
Okay, sorry.
It depends on the size of the reactor, but also it depends on the kind of fuel you have. It's different from oxide fuel, from metallic fuel, carbide fuel. The analysis could be, so you did it in oxide fuel, right?
Yes. Yes,
okay,
right.
so conclusion may be a little bit different with a different fuel. So you have to, this is the second part you have to take into account. Once again, I underline the fact that the new design sodium-cooled reactor, at least in France, will have will not have a positive void coefficient. It's a requirement by safety authorities. So, okay. Sorry, just concerning the uranium-232, I remind what I said several times. If you fabricate uranium-233 in the blanket of your fast breeder reactor, the content of uranium-232 is very low. So this kind of, is less proliferation resistance, I would say, because of the, you have a less amount of the, and my third remark is clearly that is a fact. The thorium uranium-233 performances in terms of breeding is less interesting than uranium-plutonium fuel. So if you one day in the future designing or building fast breeder reactors, what would be the interest to have thorium cycle instead of uranium-plutonium cycles in the performances in terms of breeding is much less interesting. I don't know.
You asked the question, okay.
Well, yeah.
Yeah, okay. If, in my opinion, the advantages, I don't know if I should say it, but advantages of thorium is does not allow us to consider the thorium cycle for solid fuel fast reactors, because we so big experience with uranium plutonium, and advantages probably not as strong as.
Okay, thank you. It's not only experience. Once again,
performance in terms of breeding. Yes.
Yeah. Okay, I think we should move on now. Thank you very much indeed for a very good speech.